Thank you very much. Thank you for inviting me. So before I start talking about the main topic of my presentation, I thought I would give a little bit of background of other things that I have worked on. Since Tamara was going first, I couldn't talk about images and text, but that's okay. So yeah, I did start out working on scene understanding. That was back in 2006, the good old days when we had SVMs and tiny data sets and things like that and bags of features. After that, the best way that I can summarize some of the other areas that I've gotten into is by summarizing the PhD dissertation work of the students that I've supervised. So after I graduated myself, my most consistent interest has always been in scene understanding, but I've tried to always sort of go beyond the things that we've done before and tackle more challenging problems. So with my first PhD student, we looked at image segmentation, semantic segmentation, and instance segmentation in sort of a long tail scenario for hundreds of classes where you have a lot of small classes with not a lot of training examples. And this was before the days of mass CNN, so it didn't work, but we tried. With another student, Yunxiao, we looked at large-scale image search with binary codes. It was fun for a while. Our features didn't work at all. So if you, binarize them, we had search that also kind of didn't work, but that was okay. So these binary codes, they fell out of favor for a few years after people discovered AlexNet, but now I notice that they're coming back because people realize we have really good features now, so when you binarize them, you can do this really well. And it's still a fun problem to binarize things, and in fact, I will get back to it in the thing I'm going to talk about. I just graduated 3 students this year, so I'm feeling a little bit sentimental and I don't know, like some emptiness syndrome or something. So with one of my recent students, Brian, we worked on images and text. We worked on visual grounding. So if you have sentences and images and you want to decompose the sentences into their constituent parts, the phrases that are mentioned, and look at maybe the attributes like red jacket, look at relationships like man carrying a baby, and figure out how these linguistic parts relate to what you can actually observe in the image and to inference of where all of the entities mentioned in the sentence are in the image. With another student, Liwei, we looked at deep networks for image text understanding. And we looked at the task of diverse and controllable captioning, because if you ask multiple people to caption the same image, they will probably produce pretty different sentences. So we wanted to have models that also had some diversity to them, also to reflect uncertainty. Like if based on your features, you're not sure whether an image shows a man or a woman, you want to generate some candidate captions that say man, some that say woman, and so on, maybe then you rank them somehow. Or if you can guide captions through object detection, for example, if you only detect a person, like on the left image, then you can generate sentences that say something like a man and a woman standing in a room. Whereas if you also detect a remote, then the captioning naturally changes to a man and a woman playing a video game. So that was kind of a nice deep model that we had. Last but not least, the third student who graduated this year, Arun Maria, he worked on something that I can best describe as doing stuff with deep networks. Because deep networks are fun and they work and we've got lots of data sets. So for each interesting task or data set, you can come up with a type of network with an architecture that gets pretty good results. So Arun was pretty good at doing this. He came up with a bunch of specialized architectures for specialized tasks, but then he got kind of fed up with it. So basically the situation which frustrated us was, well, we have lots of data sets, of course, ImageNet, all sorts of large scene data sets, action data sets, both for video and still images, specialized fine-grained data sets for flowers, birds, cars, what have you. And we can train networks for these data sets, but every time you sort of have to start from scratch. You have to take some network, maybe an ImageNet trained network, fine-tune it on one of these data sets, and you have a separate network for each data set. And that's not very satisfying after a while. So what Arun wanted to do was do more with less, or capture multiple data sets, train models for multiple data sets, but have a very compact representation, not require a new network for every possible task. So to make it a little bit more precise, the scenario is, let's say we've got a single network. This was our first attempt, so we just started with a single fixed architecture, like a VGG net. And tasks arrive sequentially. So the first one, of course, has to be ImageNet. So let's say we got our VGG net, we train it on ImageNet, and we've got a predictor for task 1. Now we've got task 2. We have to adapt the network to task 2, but hopefully it can still do an okay job on task 1, and so on, so forth. So we would like to adapt one network to as many tasks as possible. So there is some existing work which goes some way towards, telling us how to do it. Well, the simplest thing we can do, of course, is to just fix the initial features, fix the initial representation we get from the ImageNet trained network, and just train a new classifier layer for each new task. At the very least, we've got to do that. We've got to train a custom prediction layer for each new task. So this is pretty simple to do. We train our custom predictor on top of pre-trained features, and it's compact. So most of the network is shared, only the final predictor layer is not shared. So it's got very low overhead, basically the lowest overhead that we can have, and it's pretty simple. We know how to do this. Unfortunately, it doesn't always work well on new tasks. When a new task is very different from the original task, you need to fine-tune the lower layers in order to get the best performance. Like if your initial network is trained on ImageNet and you want to classify paintings or sketches or something pretty different. So usually with this classifier-only approach, you will not get good accuracy. Okay, on the other end, the other extreme is we can fine-tune a separate network for each task. We can initialize the network for each task, let's say with the ImageNet trained network, and just fine-tune the whole thing and have a new copy for each task. This will give us the best accuracy, just about, that we can get, but it also gives us the worst overhead. We need a brand new copy of the network for each task. And there's no kind of parameter sharing, so that's not satisfying. Okay, so if we still want to share parameters, one thing we could try to do is joint fine-tuning. So every time we add a new task, we keep all the training data around and we just retrain or jointly fine-tune the whole network on all the tasks that we've got. We try to somehow mix the training data, mix the losses or combine the losses on all the tasks and jointly train. So this shares parameters. Once again, it's as compact as just introducing a new predictor layer, but you're trying to modify all the layers to do the best you can. However, a major disadvantage is you need to keep all training data around to fine-tune the network every time, to make sure that you can learn a new task, but also still do okay on the old task. And in practice, it's very tricky to do because you have to figure out just the right way to mix the losses, to mix the data in the batches, and if your data sets are very different size, this is very tricky. And the last thing, which gives rise to some of the newer and more intriguing approaches, is sequential fine-tuning. So the requirement here is we don't want to keep all the training data around. We only assume we have access to new task data and the existing network. So there are a few methods for sequential fine-tuning that train the network only on new task data, but try to introduce some sort of constraints or regularization to make sure that the network still does okay on the old task, that the activations don't go too far from the activations of the original network in learning without forgetting, or you try to figure out which weights were important for the old task and not change the important weights too much and stuff like that. So these approaches are interesting. They share parameters, which is what we want, and we don't need to keep all the training data around, but they still suffer from something that's known as catastrophic forgetting, meaning that the performance on older tasks degrades as you introduce new tasks. And you usually can't provide hard constraints. You can't provide guarantees on how well you're going to continue to do on old tasks. You're just going to drift. So Arun and I looked at this situation and we started thinking, okay, well, what can we do to share parameters and avoid catastrophic forgetting and hopefully have methods that are clean and simple? And we were inspired by papers on network pruning, and these papers show things like you can take a VGG net and prune up to 90% of parameters and almost not lose any performance. Of course, everybody knows that by now that VGG net is kind of very over-parameterized. It's a very redundant and roomy architecture. So at the end of the day, it's not super surprising that you can prune things. To me, it's very frustrating that we don't know upfront how to train a network that has 10% of the parameters, but once we've trained a much bigger network, we can figure out how to prune it to get it down. It's one of the mysteries that are not yet solved. But we know that we can do that, so based on this insight, we thought, okay, so we know that the VGG net has way more parameters than it needs for a single task. So let's just try to stuff multiple tasks into one network. So the basic approach is very simple. We just sequentially prune a network and retrain new weights for new tasks. So the idea is, let's say we have a filter for the first task, like for ImageNet, and we prune this filter. So we prune the network by pruning every filter, meaning we get sparse filters. And we do it actually more or less just by thresholding on weight magnitude. It's a pretty simple pruning method. So you prune away some percentage of the weights that we have to specify, like 50% of the weights. Then, in order to get the best performance, we actually have to fine-tune. Given the still active weights, we have to fine-tune them to maximize performance. But if you do that, you lose almost no accuracy on the original task. So now we've ended up with a bunch of inactive weights, and we can reinitialize these inactive weights and train for a new task, like task 2, which represented here by orange. And once again, we can prune only the orange weights. After we prune them the first task, we no longer touch the weights on the first task. And the predictor on the first task will ignore any subsequent weights, so the performance will not be affected. So now we prune the weights that we trained for task 2 and fine-tune after pruning, but once again, after we did that, the performance on task 2 will stay fixed. The predictor for that task will ignore any subsequent weights, and we're not going to touch the existing weights. And we train on task 3, and each new task can use all the weights from the old tasks, but old tasks don't see the weights for the new tasks. That's the idea. And we can do this until we basically run out of weights to prune. We call this approach PackNet because we're just trying to pack or stuff new tasks into the same network. To do inference with this, we have to do multiple passes for multiple tasks. We have to apply the corresponding mask to figure out what are the active weights for the task and do a forward pass. We can't do forward passes for multiple tasks simultaneously. Okay. But that's the approach, and it basically has very low overhead per parameter. We just have to note for each parameter what is the task for which it was first used. So here are some experiments. The most common scenario that we evaluated on was starting with an ImageNet trained network and then introducing some fine-grained tasks represented by smaller data sets. We've looked at some other stuff as well in our papers. This PackNet was published in CVPR. So we looked at things like jointly training networks for ImageNet and places, but I'm not going to talk about it here. So the experiments that we did were starting with an ImageNet trained network and adapting it sequentially to data sets like birds, cars, and flowers. So here's a basic illustration of the difference between our approach and previous approaches for sequential adaptation, like learning without forgetting. So with learning without forgetting, they don't fix any weights. When they adapt to a new task, they sort of try to regularize to keep performance on the whole task similar, but they can't give any guarantees. So if you sequentially introduce tasks, let's say you introduce hubs after ImageNet, the error on ImageNet goes up in learning without forgetting. And every time you add a new task, errors on the old task go up. Whereas with our approach, after we prune, so this first red dot on the left that shows the performance in ImageNet before pruning, after pruning it goes up by 3% or something, but afterwards it stays fixed because we freeze all the weights that survive pruning. And every time we introduce a new task, the performance on that task will stay fixed as we add new ones. So that's kind of the key advantage of our approach. As far as looking at accuracy, we have the classifier-only baseline, which is just keeping the weights of the original network fixed and only training a new classifier layer. So that's the approach with the smallest overhead in terms of kind of storage and number of parameters, but the worst accuracy. So that's the upper bound. The lower bound in terms of accuracy, or kind of the thing that we want to match, is the performance of individually trained models. This is the heaviest approach, has the heaviest storage, but has good accuracy. So where do we fall? With PACnet, if we start with an ImageNet trained network and prune by 50%, the error on ImageNet goes up a little bit due to pruning, but the errors we end up with on the individual small data sets are, well, they're a little bit higher than those of individual models, but they're much closer to the errors of individual models than errors just of the classifier-only approach. What we can do also, we can prune more aggressively in the beginning. So we can start with an ImageNet trained network and prune by 75%. So we get a higher error on ImageNet, but we get lower errors on the individual small data sets because we left more room to add parameters for the small data sets. So this is the basic trend, that the more parameters you have left for a data set, the better it's going to do. And these results don't talk about the order of adding tasks. They're actually averaged over all possible orders of adding tasks. And the basic trend you have that the later you add a task, the higher is the error going to be because you have less room in the network. As far as memory or storage for the models, and actually we did this not only for VGGNet, we did this for other architectures as well. The storage is very close to that of classifier-only approach. So it's a pretty compact method, but it gives us accuracy that's closer to that of individual models. So as far as accuracy on other architectures, this was actually one of the surprises. It wasn't clear to us in the beginning whether it would work on something besides VGGNet. Because I mentioned VGGNet is very over-parameterized, so it makes sense that pruning works well. But if you look at ResNet and DenseNet, they're much more compact, so it wasn't clear up front whether pruning would still be effective. And it turns out that the trends are exactly the same, and overall, globally, it's a better network, it's more accurate, so all the errors are still lower, and we still come much closer to the errors of individual models. And in fact, we found networks like DenseNet to be more resilient to pruning. You can see that as we prune the initial ImageNet trained network, the performance actually doesn't creep up at all, which was interesting. Okay, so the biggest disadvantage of PACnet was that the performance is dependent on the order of adding tasks, and you actually have to do this pruning, and the later you add a task, the worse it's going to do, and eventually you're going to run out of room to add new tasks. So we wanted to have an approach that was ideally insensitive to the order of adding tasks and could accommodate a lot more tasks. So this approach that's going to appear in this ECCV we call piggyback. And the basic idea is that you have an initial network, like an ImageNet trained network, and you don't touch the parameters at all. only for each new task you train a new binary mask over the parameters, telling you which subset of the parameters will be used by that task. So Arun came up with this idea, and when he did, I didn't actually think that it was going to work. I said, so are you saying that an ImageNet trained network is all we're ever going to need? That this ImageNet trained network basically already knows everything that you can ever know about subsequent tasks, and for each new task you just have to figure out which subset of the weights to use. But it turns out incredibly that it's true and that it works. So the basic approach is you start out with the weights of your initial pre-trained network, which we call the backbone network. And at training time, we maintain continuous threshold values associated with the weights. And then we, at each iteration, we binarize these thresholds, and it gives us a binary mask. We can do element-wise multiplication with the filters, and it will give us sparse masks or sparse filters that are used by the network. And to compute gradients, we compute gradients with respect to the thresholded values, but use them to update the real values, the real valued weights. And then at test time, you discard these real valued weights and just use the sparse binary masks. And it's a trick. We don't really have any guarantees that it does the right thing, but it works in practice, and it's borrowed from some literature on how to train neural networks with binary weights. Okay, so then for multiple tasks, each task has its own binary mask associated with it, and every time you just apply the corresponding mask to the original network, and then you can do a forward pass. So once again, just like with PACnet, you can't do forward passes for multiple tasks at the same time. You have to do them sequentially. So now for the evaluation, we really wanted to push this method, see just how well it would generalize, really try it for large domain shifts. So we introduced a couple of data sets that we thought would be as different as possible from ImageNet. That's a data set of paintings and also a data set of sketches. The low-level statistics of these sketches, at the very least, should be really different from the low-level statistics of photographs. So once again, our baselines are the classifier-only baseline that has the lowest overhead but the worst accuracy, and the individual models which have good accuracy and high overhead. Then we, of course, also have PACnet to compare with. So when we look at piggyback does not incur any change in error on the original task because we don't touch the original network, so that's by definition. And then when we look at the performance of newly introduced tasks, we notice that in some cases it actually gets better than the performance of individually fine-tuned models. We don't know exactly why that is, but one hypothesis would be that it's some sort of regularization effect. That if you have a small data set, fine-tuning a network on a small data set is a little bit tricky. So our method where you just train binary masks is a bit more constrained, so somehow maybe it's better. So it works well. It works, once again, not just in VGGNet, it also works with DenseNet and ResNet. Although we found in those cases the performance of piggyback models is a bit worse than that of individual models. It's always better than the performance of PACnet. And we also found that we can learn task-specific batch norm parameters to basically make this difference go away. So we can look at these masks, see if they give us any insights about what's going on. We can look at the percentage of weights that get zeroed out for different data sets. And it turns out that the more different the new data set is from the original data set, the higher is the percentage of weights that get zeroed out. So for WikiArt, the percentages on the vertical axis are much higher than the percentages on cups and flowers. And for WikiArt, also, we need to zero out a non-trivial number of weights in the lowest count layers. Whereas for cups and flowers, very few weights get zeroed out in the lowest layers. So that's kind of interesting. And in general, the more different the new task is, the more weights you have to zero out. And in the higher layers as well, you have to zero out more weights. As far as the storage requirements are a little bit higher than a PACnet because you need basically 1 bit per task, whereas with PACnet you needed log of n bits for n tasks because you just need to know when was the first time the parameter was used. But it's still pretty low. If you look at the growth of the overhead as you introduce new tasks, with piggyback, it's pretty low, whereas, of course, if you just have to copy the network, introduce a new copy, as with individual models, it grows a lot. We even look at extending the method to other tasks besides classification. It turns out that it extends to semantic segmentation with a fully convolutional network, where we apply this piggyback approach to the lower layers, and then we have to introduce some deconv layers that have to be trained from scratch, but it still works okay. So we have good evidence that it can be extended to more interesting tasks in the future. So this more or less sort of concludes what I wanted to talk about. So just to summarize, once again, the problem that we looked at is how to add more tasks to an existing network while keeping, the storage overhead minimal and, most importantly, avoiding catastrophic forgetting. And we think that we've succeeded with that. Both PACnet and piggyback, they meet these requirements. They get accuracy that's very close to, and in the case of piggyback, sometimes better than the accuracy of individually trained models. And what's especially surprising to me is it works on compact architectures, especially in case of PACnet. You can still prune ResNet and DenseNet, and it works really well. Maybe because of having skip connections, it makes those networks sort of also redundant and robust. One of the biggest disadvantages with both methods is that you can't do simultaneous inference on all the tasks. You have to do a separate forward pass for each task. So with PACnet, the biggest takeaway point or insight is that existing networks are very roomy. So once again, we don't know how to train a more compact network from the start, but once we've got a decently trained network, we can figure out how to make room in it to stuff more tasks in. And with piggyback, the biggest takeaway point is that if you have an ImageNet trained network, you can get very highly performing networks for a lot of specialized tasks just by taking subsets of the weights. By the way, one of the things that we were interested in there is to figure out just how important the initialization is. Is it important that your initial network be an ImageNet trained network, or can it be anything else? And we have experiments in our paper. The short answer is yes, it is important. You have to have a sufficiently diverse, versatile initial network. We even tried to initialize with totally random weights to see if you could just zero out subsets of those and get something useful, and essentially you can. And ImageNet really works best. It's the best kind of large-scale data set we've got so far to train networks from scratch. So the most unsatisfying aspect to me of piggyback is that knowledge is not shared across tasks. A good aspect is that you can add as many tasks as you want. It never runs out of room, but the tasks do not know anything about each other. They do not interact. There's no notion of lifelong learning or building on top of what you've already learned, or if the tasks are supposed to have some synergy or help each other, we can't take advantage of that for the time being. So that's one of the most important sort of directions for future work. Others being not just keeping the architecture fixed, but maybe adaptively growing the networks as needed, adding filters, because we've noticed that basically, if you do filter-based pruning, if you decide to keep or throw away a whole filter, you can do simultaneous inference. But this type of pruning is too constrained to actually work. We noticed to get good results, we need to prune weights within individual filters, but then we can't do simultaneous inference. But if we could add filters on the fly, then maybe we could solve that problem. Or if we have different tasks that require different specialized sub-branches, then we would like to be able to have those on the fly as well. So those are the future directions, and most importantly, what I'm after ultimately is lifelong learning where knowledge in the network accumulates. So that's all that I have.